Good evening. Welcome. My name is Sandeep. I'm a faculty member at the EC department, IISc. This is EC Webinars, a new initiative of our department where we are trying to interleave our traditional faculty colloquia with distinguished lectures from speakers outside IISc. The webinars itself will run from October till February, where we'll be having 2 lectures every month till end of February. So before we get started with today's inaugural lecture, which will be delivered by Professor P.P. Vaidyanathan from Caltech, I'll tell you some logistics about the event itself. We are also streaming this event live on YouTube, and if there are any questions, there is a chat window, chat box where you can type your questions, and then I will be monitoring those questions. So we'll be taking the questions towards the end of the lecture, unless there are any pressing questions that need clarification. I'll not be interrupting the speaker. So we're also streaming this live on our YouTube channel, and it will be available in our YouTube channel for it will be saved there so that you can also watch it later. Okay, so having said that, it is a great pleasure to welcome Professor P.P. Vaidyanathan to deliver this inaugural lecture of ECE webinar. Professor Vaidyanathan is a well-known leader, expert in signal processing, expert in multi-rate systems and filter banks. He has also authored several books in this field. Personal favorite, multi-rate systems and filter banks. Many of you would have heard it. So PP did his bachelor's and master's in radio physics and electronics from University of Calcutta, and he obtained his PhD from University of California, Santa Barbara in 1982. And since then, he is with Caltech in USA since 1983. That's about 37 years now. Wow. So where he currently holds the Kyo Aiko Tomiyasu Professor of Professor of Electrical Engineering. He has also served as a department head during 2002 and 2005. He is currently a fellow of IEEE. So he has authored more than 500 papers in the areas of digital signal processing, communications, and radar. Answering many fundamental questions, groundbreaking and very inspiring papers, I should say, on several topics. And for these reasons, he has also received several prizes and recognitions. And some of the major ones are from the IEEE Circuits and Systems Society. He has received the Golden Jubilee Medal. He has also received the American Society for Engineering Education Award, named after F.E. Terman. And he has also received several society awards from the IEEE Signal Processing Society for technical achievement, education award, and also Norbert Wiener Society Award. He has received the IEEE Technical Field Award. So these are very prestigious awards. And also he is elected to U.S. National Academy of Engineering in 2019. So it's really an honor to have Professor Vaidyanathan to deliver this inaugural lecture. We are looking forward to his lecture on Srinivasa Ramanujan and his contributions to signal processing, or I should say PP's interpretation of what Srinivasa Ramanujan did, and how these are useful in signal processing. So thank you, PP.
Thank you very much.
So now, let's see, I would like to.
So you can still see my screen. Can I start now, Sandeep?
Yes, you're good to go. So thank you, PP, and it's all. The floor is yours.
Thank you very much. Thank you very much, Sandeep, for a very kind introduction. It's a great pleasure to come back to the Indian Institute of Science. I have visited you guys many times, as you know. This is the first time I am visiting you virtually, actually. First virtual visit to the Indian Institute of Science. It is unfortunate that we are all confined to our homes throughout the world, but safety first, right? So hope everyone is well. Hope everyone who is attending this seminar is keeping in good health, keeping in good stead, and getting work accomplished from homes. So let us begin by wishing well to everyone in the world. Let's wish for everyone to recover and back on their track. With that sentiment, here I am talking about Srinivasa Ramanujan's work and some impact in signal processing. Some of you may have heard some versions of this talk, but I will not assume so, because there may be many graduate students in the audience and who may never have heard this, so I will not make any assumption like that. Okay, all right. So with that, let me click this button. And, all right. So Srinivasa Ramanujan, many of you would have heard of him. Was a self-educated Indian mathematician. He grew up in poverty actually when he was a kid in Kumbakonam in Tamil Nadu. He was a mathematical genius, and the genius was not recognized for a long time. And it was recognized by some Indian mathematicians and also by Professor Hardy at Cambridge. That is Professor Hardy. And Hardy invited him to come to work with him, which happened eventually. For 5 years, Ramanujan was in Cambridge, and he really transformed the world of mathematics in many ways. That's the history of Ramanujan. And very briefly, he created history in mathematics during his period. At a very, very young age, can you believe this? He became a fellow of the Royal Society, arguably the youngest. There may be someone younger, some of you may know in the audience, but I have to look it up. He's arguably the youngest, and he passed away, unfortunately, the very next year. Many of you, especially the older people in the audience, people like myself, people a little bit younger than myself, would know a lot about Ramanujan already. You may have even read his autobiography, not autobiography, just biography and so forth. But I also recognize that there will be some of you who have not heard a lot about him, especially the younger generation, who are very preoccupied with so many other things to learn and do, right? So I will therefore spend a couple of minutes talking about him first and then talk about the work. Okay, all right. So Ramanujan, when he was young in Kumbakonam, he later in Madurai, I believe, he did not have access to education like you and I do these days. The only exposure to mathematics, proper exposure, was this book that he borrowed from the library. Okay, and without formal education, he would basically take from this book various formulas like this. The book was only a listing of formulas like this. It did not have proper introduction, proper proof of all these things. A list of formula after formula after formula. Look at that. Formula 822, 823, like that. He would take this and try to prove this by himself. And he succeeded in doing all that. And that is how he had much of his education during those days. Okay. And of course, being the genius he was, he started inventing his own identities of this kind and proving them. He used this. How many of you recognize this? All the older guys obviously would know what this is. I don't know about the younger generation. My kids would not recognize this, for example. This is called a slate. He would write his proof on the slate, record his result on a notebook, neatly written by hand, and he would erase the proof. Why? Because he could not afford to use paper for everything, right? He grew up like that. So look at the way he grew up and look at the impact he created, right? So this is called Ramanujan's slate, and he would record his proof. This is his own handwriting, okay? Ramanujan's handwriting. He would record all the proofs like that, all the final results like that. And there are several bound volumes like this. You will find it in Madras University. You will find it Tata Institute of Fundamental Research. Various places you would find these notebooks. And even the original ones are there somewhere laminated properly. OK, and later on, this becomes proper bound volumes printed properly, latex and whatnot. I will show you that later. OK, now what you see in this picture is Ramanujan and Hardy. See how handsome Ramanujan is. Isn't that amazing? I'm just kidding. This is actually from a movie on Ramanujan. This handsome young man, I believe his name is Patel, the actor in that movie. OK, Hardy, I don't remember who the actor is. Here is the movie. You can actually watch this movie. The Man Who Knew Infinity. I am sure many of you have watched it in the audience, and I am sure many of you have not watched it. So one homework I have for you is at the end of this seminar, unless you have another commitment, watch this movie today. And today is Friday. That means you have a weekend ahead of you. During the weekend, watch this movie if you have not watched it. It's a beautiful movie. I'm not advertising for the movie. I have nothing to do with the movie. I just watched it 2 or 3 times. I just like the movie. OK, about Ramanujan. With all that, back to the talk. Talk outline. I will tell you something about Ramanujan sum, which he introduced 1918. 100 years ago, more than 100 years ago, 102 years ago. All right. And I found that this is very useful for representing periodic signals. I'm not the first. Before me, some other people also knew it. I found a different way to use it, which became much more useful actually. All right. And from the Ramanujan sum, I will introduce something called Ramanujan subspaces, which really what made it useful for me. OK, so I have to talk about those. From subspaces, I will talk about dictionaries. In this modern days of signal processing, you cannot escape talking about dictionaries, sparse representations, machine learning, all that stuff. Right. So I will make connection to dictionaries. From dictionaries to filter banks is one step. OK, I will talk about Ramanujan filter banks, Ramanujan dictionaries, all that stuff. And also talk very briefly about IISc. Many of you know about the music algorithm in array processing. Very well known algorithm for identifying sinusoids buried in noise, right? There is something called IISc, which means integer music, that's connected to Ramanujan. OK, I will briefly mention all those things. I don't know how far I can get, but I'm not in a hurry to finish all these things. The goal is not to, it's not like a syllabus or something. Whatever I can finish, I will finish. Otherwise, it's OK. You can read out papers later. OK. All right. So there is no set agenda. This is more or less the outline. OK. All right. Periodic signal. All of you know that a periodic signal looks periodic, like I have shown in the picture, right? So if the period is P, this equation is satisfied. We are talking about discrete time, and therefore the period is automatically integer. P is an integer, N is an integer. OK. So the smallest integer P is called the period in discrete time. OK. All right. So I am talking only about integer periods today, which is a restriction of this talk. So keep that in mind right in the beginning, because many people ignore that and they get very excited at the end of it. Can I use it for this? Can I use it for that? Yeah, you can use it for anything as long as the period is integers. If not, you have to make some adjustments. OK, sometimes those adjustments are not very good. OK, all right. So we all know the DFT, we teach it in fresher, sophomore and junior level classes. That's the discrete time Fourier transform, right? Now, the thing about DFT is that kernel or the basis functions Eij 2 pi kn over n, that kernel, they are periodic signals. K is like the frequency index, n is like the time index. Capital N is an integer, represents the length of the DFT or the data size. OK. For example, if n is 6, these basis functions of DFT, they are periodic signals, but they do not represent all periods up to capital N. For example, if n is 6, the possible periods up to 6 are 1, 2, 3, 4, 5, and 6, right? But all these periods are not represented by the basis functions. Only those periods are represented that are divisors of capital N being the duration of the data. For example, this is the period 1 term, period 2 term, period 3, there are 2 terms. Okay, period 6, there are 2 terms and so forth. Therefore, this is one restriction of the DFT. So when you use the DFT basis functions to represent something, those basis functions don't represent all periods. They represent only those periods that are divisors of capital N, which is the DFT size or the data size. Okay. Therefore, usually we tend to ignore it because if the data size is large, it's pretty good. Okay, but in this case, data size is not large and the periods 4 and 5 are missing. Okay, so I will eventually end up showing you that the Ramanujan representation has the advantage that you can cover all the periods in that interval from 0 to n, from 1 to n. Okay, all right. So again, go back to DFT. It represents the only divisors of n. Only those periods are represented. Even if n is large, 32, there are very few divisors. You see that if n is 32, it's a power of 2, right? So the divisors are just 1, 2, 4, 8, 16, 32. Okay, so the Ramanujan representation looks like this. What I have shown in the bottom, C sub q is the Ramanujan sum. So there are n terms in that representation. Each term is an individual period. So all the periods 1, 2, 3, 4 up to q, up to n are represented. Okay, so that is the difference. Okay, now if I just stop here, this is not yet very useful. I will show you very soon. And I have to make one important adjustments to actually make this representation more useful than DFT. Okay, so once I have done that, I will show you examples. So it's very simple. Okay, all right. So continuing on the DFT, limitations of DFT. So consider a signal. This is a very toyish example. Period 8 signal, okay, like a cosine or something, or like a complex cosine, complex sine. I show the real part, okay. That's the DFT, looks beautiful, right? Very sparse representation, okay. Very sharp in the DFT point. Slightly change the period. Now it is 9 instead of 8, that's all. Now you take the period, it looks horrible. All the sparsity is gone. By looking at it, in principle, it has all the information about the original signal. But by inspection or by simple analysis, it's very difficult to say that the period is 9. It's not that the information is lost. To extract the information is not convenient. That's all I am saying. Same thing here. Okay, the another example, period 8. It looks nice and sparse. Period 9, it looks like a mess. It's completely filling the DFT domain, DFT grid, right? Okay, that's just to show DFT is not very convenient, especially when the data length is not large. If you have a large data, 1,000 points, 10,000 points, it's not a problem with the DFT. DFT works nicely, but short durations like DNA molecules, short DNA itself is long, but short stretches of DNA where there are genes, for example, protein coding genes, short stretches of protein molecules, and so forth. There we do have an issue with DFT. Okay. By the way, those of you experts in spectrum estimation, I know there are some wonderful people in your department in the Indian Institute of Science, whom I have known for a long time, who are experts in spectrum estimation and whatnot. All right, they know that spectrum estimation, light spectrum estimation, for example, there are many techniques for that. Music, spirit, all that. Right? Periodic signal, it's also a harmonic structure. It is also in principle a light spectrum estimation. But there are differences. The differences being periodic signals have a harmonic structure. Number one. Number two, sometimes we have very short stretches of data and we really cannot afford to take the usual averaging, eigenspace methods and so forth. Then how do we extract the periods when it's very noisy? So it's a different problem because of the context in which it comes. Okay. So there are all sorts of methods like harmonic music, harmonic matching pursuit and whatnot. You will see in the literature. There are theses on that way before we got into this field. Christensen and all this. There are theses on that. There is even a book monograph by some of these authors. Okay. All right. All that is fine, but all that is before we found out about the Ramanujan techniques. Okay. All right. Now, let me also mention briefly about hidden periodic components. Look at this signal. It looks nothing like a periodic signal, right? But it comes from two periodic components like this, period 16 and period 12. And the reason why it does not look periodic is that the LCM of 16 and 12 is like 48, right? Is that correct? Yeah, 48. And the data duration is close to 50. Okay, so this signal period is 48, which is the LCM of 16 and 12. And therefore, the data is too short to show the period. Okay, it's very difficult to use standard analysis and extract the information that the periods are 16 and 12. But our technique based on Ramanujan subspaces will actually reveal it. Okay, and this is just a slide showing the importance of period estimation. So many applications. Okay, I don't have to spend time on this. Now the Ramanujan sum. Before I talk about this, Sandeep, everything okay so far? Can everyone hear me? Can you hear me?
Yes, loud and clear, all good.
Thank you so much. Very good. Okay, this expression you see is called the Ramanujan sum. You know, all of you can see that. Let me see here. This thing you see here, the EJ 2 pi, that arises in the standard DFT, Q point DFT, Q point DFT, right? So I add up all those basis functions. The answer is a function of time. N is the time index. OK, I add up only over those DFT frequency index that are co-prime to Q. OK, so Q is the DFT length, that Q. OK, fixed number. You add up over all DFT indices that are co-prime to Q. You get an answer that depends on time, right? That thing is called the Ramanujan sum for that particular Q. For every Q, you have such a thing. Okay, Ramanujan wrote it slightly differently using cosines. It's the same thing. Okay, so this notation means K and Q are co-prime. So it turns out that this is a periodic signal and the period is exactly Q. What I mean by exactly Q? It cannot be a divisor of Q. Like if Q is 9, the period is not 3. It is exactly Q. Reason I'm mentioning is that if you have EJ 2 pi over Q, 2 pi no Q, Kn over Q, normally the period can be either Q or a divisor of Q. But because K and Q are co-prime, the period is exactly Q and not a divisor of Q. Okay, this can be shown. And the number of terms in that summation is the Euler quotient, which is the Euler quotient is the number of integers that are co-prime to Q and smaller than Q. Okay, if Q is 9, find all the integers smaller than Q that are co-prime to Q. That's the Euler quotient. Therefore, that sum has exactly FQ number of terms. Here is the C9, for example. It looks very nice and simple, and the DFT of that looks like it. Main thing to notice in the DFT, those DFT integers that are co-prime to Q, namely 1, 2, 4, 5, 7, 8, they have a constant height, namely 9 in this case. Others are 0. So you can think of Ramanujan sum as those periodic signals whose DFT is 0 when the DFT index is not co-prime to Q, and a constant when it is co-prime to Q. Think of it like that. That's another way to think of Ramanujan. Ramanujan didn't write it like that, but it's the same thing. All right. OK, so the main thing is what is good about it. OK, first of all, Ramanujan himself knew that this thing is integer valued. Isn't that interesting? All these complex numbers, when you add over the co-prime only, they add up exactly to integer valued numbers. He had a proof of it in his 1918 paper. Here are examples. So C6 has period 6, for example, everything is integer. C5 has period 5, everything is integers and so forth, right? OK, good. And it turns out that they are pairwise orthogonal. Take any two of them. Take the product and sum over this. Sum over what? Sum over at least the common multiple of Q1 and Q2, LCM. Then you will get 0 exactly. So there is this orthogonality property, which is also very interesting. We will find it useful later. OK, we will create basis functions. We will create dictionaries where the things pairwise orthogonal. OK, all right. Ramanujan himself was interested in profound things in arithmetic, right? Analytic number theory and whatnot. You know, there are things called arithmetic functions. For example, given an integer n, what is the number of divisors of n? Given an integer n, what is the sum of all those divisors and so forth, right? For these things that depend on little n, he found closed form expressions like this, and they were infinite series in the Ramanujan sum. How he found those, you have to read the proof in his 1918 paper. How did he prove those? You have to read the proofs. His papers are no nonsense papers. There are theorems, there are proofs, there is no pep talk. There is no talk about why this is important. Why he can raise so much money from the government to get support? No, nothing. He doesn't care. Here is my theorem. Here is my proof. End of this story, right? Clean, beautiful papers, right? No sales stock, nothing. Okay, so you try looking at this paper. It's fun looking at these kind of papers, right? It was a race of purist, put it that way. Okay, something called Euler torsion function. Remember, I mentioned to you, he could express even that as an infinite series in the Ramanujan sums. Okay, this is not the topic today, so I'm not going to talk about this again. It will take a separate talk, several talks to talk about these things. Okay, so I will not talk about this. I'll come back and mention our goal. Our goal is to use this Ramanujan sum to represent periodic signals and hopefully find methods to identify integer periods. If it's not integer periods, what do we do? That's later. That's not so easy, unfortunately. Okay. There are advantages of a traditional meaning, DFT and that sort of methods, like I will show you. Okay. All right. First, let me tell you some methods used by some other people. You know, Planath, Maindra D, Sugavaneswaran. These people, even before we knew anything about this, some of these people already used Ramanujan sums to represent periodic signals. They were not very successful, if I may say so, because they missed some basic points. Okay, I will explain that later. But let me show you the manifestation of that problem first. I will tell you briefly what the problem itself is later. Okay, and then how to fix it. Okay, again, take a toy signal, baby signal, period 6 cosine. Okay, you represent using Ramanujan summation that I have shown here. See that summation like that. Try to compute Q. There are ways to compute Q by inverting a matrix. And you will find that this is very sparse. See, A6 is there. All other A's are 0. Beautiful, beautiful, right? Sparse representation. And then take A7, 7, okay? Meaning period 7, take a different signal. Again, do representation. It's anything but sparse. It looks like that. So it's very sensitive. Sometimes works, sometimes it doesn't work. When it wants to work, it works beautifully. When it doesn't want to work, it doesn't work. Just like Wi-Fi. All of us are working with Wi-Fi from home. When it works, it's great. Great download speed, great upload speed. When you are giving a webinar, suddenly it doesn't work for 20 seconds, everything is screwed up, right? Same thing. So we want to fix this. So what we did was we introduced something called Ramanujan subspace for this. Okay. I am saying this is not a good way of doing it yet. OK, this was before we knew anything about this. So I'm saying it's not a good representation. I am also putting a smiley face. Is that a typo? It's not a typo. Whenever you find in the literature something that doesn't work, you are very happy. You know why? Because you can do some work finally, right? You can do something to improve it. You can publish your paper. You can give talks. Great stuff, right? OK, so that's the meaning of smiley face. Smiley face means I have something to do. That's what it means. OK, what do we do about it? OK, we replace each Ramanujan sum with a subspace. The problem with this representation, as you see it, is that each CQ represents only a one-dimensional space for a period Q signal. But period Q signal requires more than a one-dimensional subspace. This is the problem. The dimension you require is exactly phi Q, where phi is the Euler torsion function. This is not obvious. Don't worry if it's not obvious to you. It's not obvious. It takes proof. OK, by the way, be careful. The set of all periodic signals with a fixed period, period Q, for example, is not a subspace. Meaning, if I add two period Q signals, the answer is not necessarily period Q. The answer could be period Q or a divisor of Q. Therefore, it's not a subspace. But still, there are subspaces of periodic signals that are not the entire period Q set. Those are called Ramanujan subspaces. I mean, we define it like that. OK, so I will come to that later. So my idea, therefore, is to replace this CQ with an entire subspace and therefore create a union of subspaces. And that is how the dictionary comes about. OK, so those ideas are familiar to many of you in the audience already. So I just made the connection. So very, very simple in that sense. OK, but it works beautifully. OK, what is the idea now? I will introduce Ramanujan subspace to replace those CQs. And then that is, so I have to define what this means. OK, that leads to not only a nice representation, it is very useful to identify periods, identify hidden periods, even when the data duration is very small, 100, 200, 50, all that stuff. It works very nicely, even when there is noise. OK, even when there is streaming data and the period is changing with time, you can do something called just like wavelets and stuff, we can do something called Ramanujan filter banks that gives a time period plane plot. All that comes up later. OK, but what is the basic idea? Basic idea first. Ramanujan subspace was introduced in 2014. We can read it up. Basically, idea is this. Consider signals that are linear combinations of that DFT kernel. See this WQKN. K is the frequency index. Q is a fixed number. Think of Q as a fixed number. Q is 9, for example. N is the time index. So this is a signal function of time. OK, this signal function of time. Consider all the collection of such signals. For a fixed Q, you do the summation again over coprime frequencies. Got it? For a fixed Q, do summation over coprime frequencies, and AK are arbitrary. Therefore, these are linear combinations of that kind. OK, linear combination only over coprime. All such linear combination, right, is a subspace. That subspace is called the Ramanujan subspace. So this is a complex basis for the subspace. OK, so those are the DFT columns that are coprime to Q. It turns out, not obvious, but it turns out that the same subspace can also be represented using integer basis functions. This is CQ, the Ramanujan signals, which are integers, and shifted versions. Finite number of shifted versions. How many? Pq, where Pq is the Euler quotient. OK, it can be shown that this also forms a basis. So these are all circularly shifted versions. Circularly, I don't have to say because these are periodic signals, period Q, right? OK, so this also requires proof. It's there in that paper, 2014 paper. OK, so this is real integer basis. So these are subspaces with that real integer basis, equivalently complex basis. OK, so the main thing is what are the properties of this? Why is this any good? OK, and the subspace has a dimension pq, which is the Euler quotient function. OK, now, for example, look at that Ramanujan's itself. OK, C9 is a 9th Ramanujan sum. This is the DFT. Remember that DFT is 0 when K is not coprime, and it's a constant when K is coprime to 9. Remember that? OK, now instead of this, you consider signals like this. Again, the DFT is 0 when it's not coprime, but when it is coprime, the DFT instead of being constant can take any possible value. Take the collection of all those signals. That is exactly the Ramanujan subspace. OK, so it basically generalizes the Ramanujan sum, and therefore the Ramanujan sum trivially belongs to the Ramanujan subspace, right? OK. Equivalently, take the DFT matrix, Q by Q DFT matrix, right? There are Q rows, Q columns, right? Take those columns whose indices are coprime to Q. These are the coprime to Q, coprime to 9, right? The subspace spanned by that is the Ramanujan subspace. That's it. That's the definition. Very simple definition. CQ is simply the sum of those columns. The Ramanujan subspace is any linear combination of those columns. That's the only difference. OK, all right. Now, based on that, some theorems. But what good is this, right? That's the main point. Any non-zero signal in that Ramanujan subspace has period exactly Q. Being a subspace, 0 is obviously a member. That's obviously not periodic, right? It is trivial, right? Degenerate. OK, so period exactly Q, meaning it cannot be a divisor of Q. If Q is 9, the period is exactly 9 and not 3, not 1, exactly 9. And any period P signal can be written as a summation of signals belonging to Ramanujan subspaces, where those subspace indices are divisors of P. For example, P is 10. What are the divisors of 10? 10, 5, 2, and 1, right? Did I miss anything? 10, 5, 2, and 1. So a period 10 signal can be represented as a sum of period 10 Ramanujan signal, period 5 Ramanujan signal, period 2 Ramanujan signal, period 1 Ramanujan signal. OK, exactly, it can be represented. And those Ramanujan components belong in a subspace, even though the period P signal collection of all period P signals is not a subspace. Still, the Ramanujan components which make up that signal belong in subspaces, Ramanujan subspace. See the distinction? That's very important. All right. Moreover, take any linear combination, any sum of things belonging in Ramanujan subspaces like that. OK, XQM belongs in the QMth Ramanujan subspace. You add them up, you get a periodic signal whose period is exactly the LCM of those indices. It cannot be smaller again. Take the LCM, period is exactly the LCM and not a divisor of LCM. That LCM property is what really makes it useful to find periods. Otherwise, you will have ambiguities in the answers. It's a very important thing. OK, when I say the period cannot be smaller than this, it's an important thing. Otherwise, you won't get unique answers at all. OK, all right, good. Now, I will talk about the so-called Faraday dictionary, which is the way you actually identify periods. OK, what it is that instead of constructing a basis, we construct a dictionary. Remember, in the beginning, I mentioned that one problem with DFT is that the basis functions contain only those periods that are divisors of the data length, and therefore it's very restricted. If we want to include all the periods that are less than or equal to the data length, you make it larger than a basis, meaning you make it a frame, or equivalently a dictionary fact matrix. OK, this fact matrix, see between the green lines, what you see is Ramanujan subspaces. OK, for example, OK, this S3 is the third Ramanujan subspace spanned by those two DFT columns in the 3x3 DFT. These come from the 4x4 DFT. You periodically repeat it until it is long enough, matches the data length.
Professor Vaidyanathan, just to,
yes.
Are you writing something? Or
I'm not writing anything.
OK, OK.
Can you still see my matrix?
Yes, I can see your slides and I can hear you. Just wondering if you're writing something on the slides.
Not at all. Okay, I'm not writing. I am just using my cursor to move it around. Can you see my cursor moving?
Yes.
Yeah, that's all I am. I'm not writing it.
OK, OK.
Yeah, when I talk, maybe it seems like I'm writing, but don't worry. If you don't see any writing, it's not your fault, right? Because I'm not writing anything. OK.
OK, thank you.
Okay, good. Yeah. So what's going on here is that S5, for example, those columns come from the 5x5 DFT. Those are the coprime columns. I repeat it enough to match the data. That is how I form the dictionary. This is called the Faraday dictionary. Similarly, I can form the Ramanujan dictionary. Instead of using the DFT basis functions, if I use the Ramanujan sum and the cyclically shifted versions, I get the Ramanujan dictionary. That's the only difference. OK, I will use this to represent periodic signals. OK, so what happens is, see, the frequency is represented by those columns. For example, W4 represents the frequencies from the 4x4 DFT grid, 4x4 DFT grid. And those are the coprime frequencies from that. Similarly, these are from the 5x5 grid, right? Take the union of those, that's called the Faraday frequency grid. It's a non-uniform grid because it's the union of all the DFT grids 1, 2, 3, 4, 5 up to 6 in this example, right? So it's clearly a non-uniform grid. OK, got it. OK. Now, these are just examples of Faraday frequency grids. I will use these in the dictionary representation for periodic signals. OK, now, for example, this is the same thing, except instead of using the DFT columns, I am using the Ramanujan sum and shifted versions for the basis, just because it looks beautiful, not necessarily any advantage. OK, all right. Now, I will use this to, OK, the total number of columns happens to be the sum of all those Euler functions. It's secondary. Don't worry about that now. OK, so let's not worry about these details. These are secondary. So let me tell you what I will do with this. That's more important. OK, so I want to represent a signal using this dictionary. X is the signal, which is either periodic by itself or it has periodic components. Representing using this dictionary using a sparse representation, and supposing after so you solve for y using standard L1 approach, right? Lasso, whatever you want, orthogonal matching pursuits. Use something to find y. But having found y, in that representations, there are columns of A, right? Depending upon which columns of A are participating, supposing S3 and S4 participate in the representation, then the signal contains period 3 and period 4. If S2 and S5 are participating, it contains hidden period 2, hidden period 5, and so forth. So we end up getting a summation like I have shown here. X of n is the summation of xq1, xq2, like that. Based on that, I can tell those are the hidden periods. OK, and I can find the period to be the LCM of those. That is the basic technique. Let me show you examples. Okay, let me show you some examples. For example, okay, Sandeep, everything good so far?
Yes.
We are connected and you can still hear me loud and clear, right?
Yes.
Great. Thank you, Sandeep. All right. So take this signal, which looks like basically a piece of crap, right? The reason for that, it is a piece of crap, meaning it's a toy signal generator on the computer. It does not look like periodic, but it turns out it is nothing but a sum of three periodic signals, 3, 7, and 11. Happen to be prime numbers, but it has nothing to do with anything. Okay. All right. The DFT, you can analyze and try to find the periods. It's very difficult to do it. It's not that it's impossible because DFT is an invertible transform, so it has all the information, but very difficult to extract it. But using this Ramanujan dictionary method, you get a so-called strength versus period plot. You can beautifully see that those three lollipops, you see lollipop 3, 7, and 11 clearly show the period. So this is the advantage of using that union of subspace dictionary, which is the Ramanujan subspace dictionary. Very simple example. Okay, you see that name there, Tenati, Shrikant Tenati. He was my PhD student when he did this work. I started off this work in 2015 or 14. He came after that. He joined me. He did a lot of things after that. And this was one of the examples he produced. He graduated a couple of years ago. He is working with Amazon Web Services now. Okay. Another example, period 7 and 10. I'm showing this for some reason, I think. Let's see. So this is using Ramanujan dictionary and also the Faraday dictionary. In both cases, you will see these lollipops clearly show the period. Okay, see, in addition to 7 and 10, here you also see 5 and 2. Why is that? 5 and 2 are divisors of 10, right? So whenever you see divisors of 10 like that, you can drop them from your calculations. The periods are only 7 and 10. It does not make sense to say this signal has period 10 and period 5 because 5 is a divisor of 10. Therefore, 5 corresponds to a harmonic of 10, and therefore it just gets sucked up in the period estimation, right? That's the idea. Okay. Okay, what is the big deal about Ramanujan versus other methods? Okay, first of all, this actually works better when the periods are integers. Like DNA sequences sometimes have periodicities in the protein coding regions. And also in the so-called microsatellite regions in DNA, there are periodicities. Microsatellites are very short DNA segments with short periodicities. Very difficult to find them using DFT and whatnot. Even proteins, which are sequences of amino acids, they also have periodicities in the regions where there is so-called hotspots in the proteins. Okay, that's where the enzymes bind to other molecules. So in those cases, periods are integers, or the data length is short, or there are multiple hidden periods whose LCM is too large, comparable to the data size. There, this method works better. Okay, all right. Now, again, on the lighter side, maybe by the time it got a little bit heavy, especially for the benefits of students who are not up to Ramanujan, I will tell you one short thing about Ramanujan life. Okay, famous taxi cab number story. All the older folk, you know it. You can go to sleep for the next 3 minutes. Okay, the younger generation, students especially. The famous taxi cab number. What happened was Ramanujan was in the hospital fighting TB in Cambridge. So Hardy came to see him, make him feel good in the hospital. Hardy wanted to divert Ramanujan's mind to about mathematics. So he said, you know what, Ramanujan, I came in this taxi which had this number 1729. Oh my God, what a boring number this is. Can you see any beauty in this number? Sometimes numbers are so boring. Then Ramanujan says, Hardy, this is one of the most beautiful numbers I have seen. Don't you see this, Hardy? It is the smallest number integer that can be written as a sum of 2 cubes in 2 different ways, like this and like this. Hardy was like, what? He was dumbfounded. How on earth did Ramanujan just look at this number and figure it out? For a long time, Hardy didn't know how Ramanujan could work it out like that on his TB bed, basically, just like that. You and I explained by saying that he is a genius, but Ramanujan was also working on so many of these representation problems, Diophant equations and so many other things. So this was part of some of those things he was working on. Okay. Well, the older folk know this story. Some of the students may not believe it. If you don't believe it, I will even show you the taxi cab. There is a taxi cab. See the number on the top? That's the taxi cab. I'm just kidding. OK, this is from the movie. If you watch the movie tonight or over the weekend, you will see this taxi cab somewhere in the movie. OK, right. Ramanujan notebooks. How many of you have heard this? You know, I showed you that slate and the handwritten stuff, laminated and kept in some libraries in India. People have converted that into books. Bruce Brunt created these books. Part 3 means there is also part 1 and part 2. They are collections of formulas that Ramanujan wrote down, some with proof, some without proof. So whenever he had no proofs, people have found proofs and written it down. They have published papers based on the proofs. People have gotten their tenure based on the proof that they found and so forth. There are 3 volumes like that. And there is also this Ramanujan's last notebook. This is the work that he did after he came back to India in his deathbed. He was still working in Tamil Nadu, Kumbakonam possibly. Working in his deathbed, papers scattered all around the bed. After he passed away, his wife collected all those papers, sent them to Hardy. Hardy didn't pay attention for it for several months or maybe a year or so. Somebody else found it after that, and George Andrews eventually properly compiled them, wrote down the proofs of a lot of missing things. And then there are several volumes of this, part 1, part 2, part 3, and so forth. I met these 2 gentlemen in London 2 years ago when there was a celebration for Ramanujan's 100th year of Ramanujan becoming the Fellow of Royal Society. There was a celebration 2 years ago. These 2 gentlemen gave talks. I gave a talk there and I met these gentlemen. It was a really hair-raising experience talking to these great people who put together all Ramanujan's work into beautiful books that is world famous today. OK, coming back, tracking periodicities as it changes in time. So you tell me, hey, PPV, you give all this talk about finding periodicities, but in my life, period changes with time, which is very common, right? Period is 5 somewhere, and then period became 11 and 14 and whatnot. What do I do in those cases? Then there is a way to do this. You simply create a Ramanujan filter bank, which will track periodicities as a function of time. Okay. For example, this is the output of a Ramanujan filter bank time period plane. Okay. In some places you see period 5 showing up. This is because there is period 14 and 11 there. 7 is a harmonic of 14, right? Because 7 is a divisor of 14. Therefore, in the frequency domain, 7 would look like a harmonic of 14. That's what I mean. OK. So that's what the Ramanujan filter bank does. Therefore, the time domain variation can be nicely captured by this. So what the filter bank is simply, you take the Ramanujan sums and make filters out of that and create a filter bank like that. And the theorem is that supposing those filters with non-zero outputs are Q1, Q2, Q3, and so forth, those are the filter indices. Then the actual period is an LCM of those. And from Q1, Q2, Q3, you can find out what the hidden periods are. You just collect all the Q1, Q2, Q3 that light up in this business, divide them into groups such that within each group, no number is a divisor of another number, right? From there, you can figure out what are the hidden periods. This is kind of slightly complicated, this technique. And because we are running out of time, I am not going into details of this, but it's all very clearly written down in our papers. I also wrote a paper after the Royal Society Centennial for Ramanujan. I wrote a tutorial on this, published by the Royal Society, Philosophical Transactions of the Royal Society. That's a very readable paper, which has all the theorems, but not all the proofs. So it's very easy to read it. I recommend that to all of you to read. Okay, you can easily read it within a couple of hours. It's a very light reading, but it has all the mathematics without the proofs. Proofs are there in the other journal papers that we wrote. Okay, all right. Now I think now that we are slowly running out of time, I will be fast on this. We had Ramanujan FAR versions of those filters. There are ways to express those in a very elegant fashion, which requires no multiplications at all. in implementation. Here is a multiplier-less implementation of that filter. My background 30 years ago is on digital filters, how to implement complex digital filters with integer coefficients, no multiplications, and so forth. Based on that, I was inspired to do this work where I could find a structure with absolutely no multipliers involved. Look at that. The T matrix has only zeros, ones, and minus ones. All the other components are absolutely trivial in complexity. So you can implement the entire Ramanujan filter bank based on this. And the output generates those subspace elements of Ramanujan subspaces, right? Okay. So it's a very beautiful structure, generates all those, and you analyze the outputs, take the LCM and whatnot, you can find the periods, right? It's very nice. And for protein molecules, this example has a period 5 component and the time period plane. You see around period 5, there is this strong signal. Okay, and so forth. That's the amino acid domain. And my student went through lots of those proteins and made a long list of all the other methods. You see on the top, all the methods that examples are shown here. The Ramanujan filter bank is the only method that succeeds for all those things that are listed here. Other methods, sometimes they work, sometimes they don't work, like the Wi-Fi we have. Okay, now iMusic, I probably don't have much time, so I will. So the standard music spectrum is well known. Okay, basically here, let me skip this one. Okay, what it is that it computes something like a music spectrum. The difference is instead of the standard Vandermonde vector that we have in music spectrum, we use vectors from the Ramanujan dictionary or the Faraday dictionary. That's really all we do. Okay, sorry for speeding this up. For example, here is a signal buried in noise. You don't see any periodicities. Standard music pseudo spectrum, very difficult to estimate period from there. And the Ramanujan music will produce beautiful lollipops like that, from which you can estimate the periods, right? You don't have to keep all the lollipops. Everything that's a divisor, you just drop it, and then you will get simplified things from which you can identify this. Okay, that's what it is. All right. So with that, currently we are working on all these other things, on integer periods, denoising applications. CNN is not the famous CNN news channel. CNN stands for convolutional neural networks. Okay, there are connections between those and Ramanujan, which I'm obviously not having any time to talk about today. Okay, so let me skip all these things. We have a website on this called the Ramanujan Periodicity Project. You will find papers. You will find MATLAB codes if students want to try your hands. We have MATLAB codes for some of this. All the plots that I showed you today, you can generate exact same plots from this software yourself as a starting point. After that, you do your own research. You apply it for your own data. Okay, to make it easy for you, have all these things here. And Shrikant Tenati was one of my students at that time. Here is his picture. Very bright, brilliant young man from IIT Mumbai. And when I started the work, it was at a point where it was not looking practical. He introduced the so-called nested periodicity dictionaries. He worked on the Ramanujan filter banks. He did a lot of, he did the iMusic work and so forth. So he made all this much more practical, much more attractive. These are some of our papers. You can read them up later, but first watch the movie. That's easier. Okay. All right. Last slide. Hardy. Remember Hardy, the mentor to Ramanujan for 5 years in Cambridge. The only man who recognized Ramanujan's genius when he was not yet well known. Okay. When Hardy retired, he said, I don't want to do any more mathematics. I'm retiring. He wrote books on philosophy and stuff. He wrote a book like this, A Mathematician's Apology, 1940. Yeah, I strongly recommend this book to everyone. Watch the movie first. After that, read this book. Now we are all confined to home. We have a lot of time, right? This book, there are PDF versions you can find. Okay, it's a very entertaining book to read. Okay, and I'm sure some of the older folks have read this book. Hardy said, you know what? The real mathematics done by real mathematicians is almost totally useless. What he meant was the real non-trivial stuff, the non-trivial stuff that Hardy would do, Weierstrass would do, Cauchy will do, all the greats, Riemann would do, Gauss would do, real mathematics that the real mathematicians would do, according to him, is actually useless. What he meant was no practical application, according to him. 1940, okay. His words, not our words. You and I won't say that. Okay. Hardy also went on to say that applied mathematics, meaning the mathematics that you and I love all the time, right? Compressive sensing kind of mathematics, even information theory kind of mathematics. According to Hardy, all the mathematics that we find useful are trivial. Okay, he said applied mathematics is useful, yes, but it is trivial. So he also said the real mathematician doing the real mathematics has a clear conscience because he or she did not create any application. He or she did not try to blow up the world by, creating some violent applications of mathematics. Pure and simple applications, no applications basically, according to him, right? According to him, applied mathematics is useful but trivial. See, today you and I obviously don't agree, right? Starting from the days of Shannon, how many wonderful applications of pure mathematics we have found, right? Finite field, finite rings, coding theory, and more recently, compressive sensing, for example. So much beautiful, very non-trivial mathematics, changing the way we live literally, right? So this community of engineers who take mathematics, very serious, deep, non-trivial mathematics, and turn it into something that will actually touch our lives. You and I should be proud to belong to this community. This fantastic legacy last 100 years, maybe, starting from Shannon, even before him, Nyquist. That legacy of people who are mathematicians who would not do math just for math's sake, but to do math just to change our lives, the way we live our world. We belong to that proud community. So may God bless this wonderful community. May God bless this world. May God bless us all to keep us all healthy and happy. Okay, thank you very much. With that sentiment, I conclude. Thank you, Sandeep.
Thank you very much, PP, for this very inspiring and wonderful lecture. Now I open the floor for questions. So if you have any questions at this point, you can type it in the chat box, Q&A chat box. I can convey it to PP and we can hear his comments. So I already have a couple of questions, out of which I did miss it, I should say. And I should apologize for asking you to come this early and give this lecture on your birthday today. So very, very, very happy birthday. And so that was one of the comments from somebody anonymous. And so I also have one more question here. It's regarding the representation learning that you mentioned. So the question is the representation exactly sparse, or are the residual components close to zero?
Very good. That's a very good question. The residual components are exactly zero if there is no noise. And the residual components won't be exactly zero, typically for two reasons. Either there is noise or the data length does not have an integer number of that periodic component. In those situations, there is that residue created. So that's a very good question in that sense. So even if there is no noise, sometimes that small residue can be created because of that. So that's the question to that. That's the answer to the second question. As for the first question, which is more of a comment, thank you very much for remembering my birthday. So this anonymous person, I have no idea how he or she knew my birthday. Thank you very much. I am very touched. All right. Any other questions, Sandeep?
Yes. Sanchit says very interesting work, sir. Can we use this technique to obtain time frequency plots of EEG signals?
Okay, yeah, this is an interesting question that often comes up. Yes, in principle, yes, in the following sense. You see, if you take a continuous time signal, speech, ECG, right? What music, right? Take a continuous time signal with periodicity or periodic components, sample it and convert it into digital. That signal will look periodic if the sampling rate is large enough, right? But the period may not be exactly an integer. Period could be 7.9, for example, 7.5, for example. or exactly 7 or exactly 13, right? All of that is possible. If the period happens to be exactly integer, which is very rare, very unlikely, right? It depends on the combination of period and the sampling rate, right? If the sample spacing and the period have an appropriate relation, then the sampled version is exactly integer periodic, otherwise it is not. And this exact relation between sample spacing and the period is impossible to achieve because ahead of time we don't know the exact period, right? Okay, so in general, the first sample versions don't have exact integer periods, but if the data length is large enough, it can be approximated, and therefore the method can be applied. But if the data length is not large enough, right, you have only 50 points and the period is 13.5 or something, it won't work that well. So this is one thing that is still on our list. What happens if the period is not integer, but somewhere in between two integers? How do you modify it so that it works almost as well as it now does? So this is still an ongoing issue at the moment. Okay, so that's my short answer to the short question, kind of long answer to the short question.
Okay, so one more question / comment from Professor Mrityunjay from IIT Kharagpur.
Yes.
He wishes hi to you, and yeah, it was again wonderful and inspiring to hear from you. Question: how does this RS Ramanujan subspace stand in terms of computational costs? In case of DFT, we have fast algorithms. Also for real signals, we need half the computations. So I guess he's expecting your comments on the computational complexity of the algorithm.
Yes, very good. Hello, Mritin. Very nice to hear from you. Hope you are doing well back home. Now, very nice question indeed. It's a very important thing to think about complexity. First, I want to again remind everyone that we are not doing a basis but a dictionary, which is an order of n square number of columns, right? And we are doing a sparse representation. So we are in a completely different world now than computing DFTs and inverse DFTs. So the complexity is comparable to any method that would do a sparse recovery kind of algorithm. You know, complexity of an L1 method, complexity of lasso, complexity of orthogonal matching pursuit. Any of those methods is equally applicable, right? So the complexity is the complexity of one of those myriad methods we choose for this particular case. So complexity is not inherently part of any of our theory or something, just a matter of which method you use to solve the sparsity problem. All right, so that is my.
Okay.
Okay.
So I think there's one more question, and after this we can perhaps end. So is there any requirement for signals to be uncorrelated for iMusic to work? I guess the question is towards can we do spatial smoothing for iMusic as well?
Wow, this is a very good question. Yeah, so the answer is yes, actually, because this signal being a time domain signal, eventually the music we do requires slight modification, which we always do for time domain music. That itself is not a big deal. And the components here are periodic components. Okay, and yes, indeed, if the data length is large enough and the periods are not too close, then some assumption that is somewhat similar to the uncorrelated assumption automatically kicks in and it works very well. And indeed, when things are too correlated, the spatial smoothing kind of ideas can improve it. That's a very good question. Spatial smoothing and its variations may be applicable here. We have not tried it. Therefore, this is very interesting. So the lady or the gentleman who brought up this question, this is a good question. Feel free to try this or find a student to try this. It's a very interesting question and let me know how it works. It's a nice idea, I think. Very nice thing to try. That also reminds me, going one step further than spatial smoothing. In recent years in array processing, sparse arrays have become very interesting. What people do is they take a sparse array, which is different from a ULA, and sparse arrays create ambiguity in identification of DOAs. So they create something called a co-array, and sometimes the co-array becomes a ULA even though original array was sparse array. And the co-array is nothing but computing autocorrelations. And it is a much more powerful technique than doing the spatial smoothing kind of idea. And the co-array technique can be used to identify order of n square sources from only n sensors. One question that came up a few years ago from some student in my group, can we do something similar to this method also when we use the IISc kind of technique? IISc kind of technique. Answer is we do not yet know. That is one question we have not yet taken seriously. So we have to formulate it properly, make proper sense out of that question. So I just wanted to mention this. That's all. So good question. Thank you for a good question.
So that it was a guy called Prasad who asked that question.
Very good. Thank you.
Okay, so I guess we will leave it at that. PP, thank you very much for accepting our invitation and giving this very inspiring talk. Once again, many more returns of the day, and stay safe.
Thank you, Sandeep. Thank you, Sandeep. Thank you very much for everything, and I'm glad that everything went very well. We were properly connected throughout the thing and so forth. It was wonderful getting back to you people. OK, so Sandeep, am I good to what do I do now? How do I? Yeah, can you guide me a little bit here? How do I unshare?
So I'm going to end the session and then I'll help you.
Yeah. Oh, I see. OK, very good. Thank you.